from UnrealTek.net, a division of BlenderTek.com again. Today we're going to be adding a basic torque curve similar to the way the stock wheeled vehicle class blueprint does. We will also be calculating the velocity of the car and displaying it in kilometers an hour, and showing physics issues we now run into now that we have actual acceleration and RPM and torque over RPM. And we'll look at some more things that we can simulate to fix this and other math and things that we can do as we move on with this project. So with that said, open your project and remember, create your way. So our goal today is to get this effect. So we'll be able to get idle torque, and as we sit idle, basically we can roll, but we have no forward speed. We can steer, but as we hold down W, we get more and more torque until it peaks out, and when we let go, it goes down to a certain amount, and we can steer. And since we have acceleration in a much different way now, plus a torque curve, we can drive much more realistically. Also, if you remember last time when we started going this direction backwards, all of a sudden we started accelerating in the inverse direction because the forward vector all of a sudden became backwards because we were just applying it to the y direction. But this time we're actually going to use proper vector math to apply torque. And we're going to apply our angular impulse rather in the proper way rather than not taking mass into account, and we're going to make a nice cockpit view. So let's get started with that. I'm just going to reset the blueprint back to its original values and we will get going. Actually, rather, since I don't have an original copy of the car, since my recordings failed a couple times now, I think it'll be easier to just go over the changes that I made. So we're gonna need some new variables. We're gonna keep engine torque as a float of 0. We're gonna keep current gear with a default value of 0 and integer. We're gonna keep torque per gear as an integer. Actually, we can delete that one. We don't need that anymore. Steering torque, we're going to keep that, although we're not using it, so we can actually delete. Oh no, it is in use. Okay, so we're going to keep that default value of 500 float. We're going to need a new float called RPM with a default value of 500. We're going to need a new boolean called B is accelerating with a default value of false. We're going to need a new float called idle RPM with a default value of 500. We're going to need a new float called acceleration factor with a default value of 6,000, which should be the same, I found, as a new float called RPM limit, which is set to your RPM limit. I've set it to 6,000. And you'll need a vector set to 0, 0, 0 called current velocity. And lastly, we will need to create a variable called engine torque curve of type curve float, and we need to create that. So for now, just leave it empty. Let's create that. So all you do is right click, go to miscellaneous, and choose float curve. Just for example purposes, I'm just going to call this engine torque curve tut. Just leave out the tut part. All you need to do is look at it as two axes, because that's how this works. You have time, which is the bottom one, and you have value, which is your y or your up axis. So you have up and left and right and up and down axes, which give you a value, and time. So we're going to use time as RPM. So basically right here would be 9.9, 10 RPM basically. And we're going to use this as our torque. So right here would be like 20 torque in whatever units. However, I found you need very high values. Of course, your time is going to start at 0, so make a new key by right clicking on the red line and choosing add key to whatever you've called it, engine torque curve. Then make time 0, so that's 0 RPM, should be 0 torque obviously. Then create another key and then drag and select only it, so only it is yellow. Then set time to something like a mid-range, something like 4500, and set its value. I think I set mine to about 65,000. 60,000. Okay, yeah. So hit fit horizontal and fit vertical so that you can always get your units in if you lose them. So yeah, we want the 4500 one to be about 60,000. So that's 60,000 Newton centimeters. We can do the math later to convert it to foot pounds for the Americans and Canadian halfish, whatever you want to do. But since most of the world, and in myself being Canadian, I should be using metric, we'll be working in centimeter newtons, which itself is a very unusual unit. And then you want to add one more, which will be at your rev limit. I'm going to go just above 6,500, and that should be back down to 0. So if you fit horizontal and vertical, horizontal, vertical, oh, okay, yeah, I'm going to select all the points. Then you have a torque curve that looks something like that, which if you create a default wheeled vehicle class, looks strangely like their default torque curve, as you can see. There's peaks at 2000 RPM roughly, but as you can see, they use the exact same setup. So we're just duplicating that essentially. So once you have that done, you can save it. I'm going to delete this extra one. And then go into your blueprint and set your engine torque curve to that torque curve. It'll be in this drop down list once you've hit compile once. So once that's done, we need to make some changes. First of all, for our steering. No, sorry, that stays the same. But moving forward and changing gears. So let's start with changing gears. We applied that to Q and E. And what we did was we decremented and incremented accordingly. And then we set engine torque based on current gear. All we're doing now is just incrementing and decrementing the values. Nothing less, nothing more. So that's all you need to do is just set Q to decrement current gear and E to increment. You can get rid of the rest. We're going to actually calculate the engine torque based on RPM now. Secondly, add angular impulse. Before we were adding it, we had it with the struct split. We were just adding it to the Y straight from engine torque. We're doing a little bit differently now. We're going to right click and recombine that struct pin so that impulse. We're going to uncheck B velocity change, so that should be false. And what we're going to do is we're going to take wheel rear left, and the reason I choose rear left is because it is not rotated, so the vector math doesn't get all wonky on us. It's easy to fix, but it's just easier. So I go from wheel rear left. If your wheels are identical and don't need to be rotated, it doesn't matter which one you choose, but you need to choose one that does not turn. If all four wheels turn, you have a bit more complicated math to do, and we'll get to that in a much later episode when we start dealing with tanks and all sorts of weird multi-wheeled vehicles. But what you want to do is drag off and type get right vector. So that is going to get the y-axis, but it's going to be the y-axis in world space, whereas before we were adding it in local space. So this will always provide the proper amount direction, whereas before it got reversed and even decreased as we got closer to 180 degrees. When we were at like 100, or when we were at like 90, our torque, or our angular impulse rather, was halved. That won't be an issue anymore, and so it'll be much easier to drive. So what you want to do is you want to take get right vector of your rear left wheel, then you want to multiply by a float, and then just plug in engine torque and plug that vector into impulse. Then what we need to do is we need to take our new B is accelerating Boolean and in between the branch where we check if it's equal to 0 and check if it's equal to 1, we need to set it twice. So if our axis value is equal to 0 true, then we need to set B is accelerating to false. If it's not equal to 0, false, then that means that we are accelerating, and you want to set that to true, and then go into the next branch. And even better yet, if you want to make some sort of engine braking effect, you could put this after the branch in the true before the add angular impulse. But we need to make sure that we are setting B is accelerating to true when we're holding down W and false when we let go. So that's how that works. And then we can move on to we might as well just do the easy part here first. So our cabin camera. So all I did was I added a new camera called Cab Cam, and I set auto activate to false, and then I placed it about where the driver's head would be. As you can see, I scaled it down also to a quarter. And then all we did is actually I'm going to replace this now. Go to edit project settings, and let's actually go to input and action mappings. We have switch camera here, which is tab. If you don't have that added in there, add another one called the gear up, and let's set that to E. And then let's do another one, gear down, and set that to Q. That way we actually have actual input actions events. Then let's export that just for backup's sake. So what we can do is type in input switch camera, and then have that go into a flip-flop. Just search flip-flop if you've never used it before, and control drag in cab cam. Control drag in cab cam and camera. And you can rename camera external cam if you want. I find that makes it a little bit easier. And then all we want to do is on A, we're going to activate cab cam and then deactivate external cam. And on B, we're going to activate external cam and then deactivate cab cam. It's very important what order that's in. Handle camera switching between external and interior cam. All right, let's go to our changing gears too, and let's move this to the right, make everything nice and neat. Let's bring it up, why not? Let's comment this, handles applying, or handles steering. Let's do this. So let's change this Q and E. So Q is going to be gear down. So input action gear down is going to decrement. And gear up is going to increment. Come on. So we're going to comment that handle gear up / down. I'm just gonna compile and save while I'm at it. All right. Then we have our move forward that we changed a little bit. Let's clean this up a little bit here. We'll go like that. Get the vector like that. We can take these and bring them over. Let's go like that. How about? I'll bring this one down, leave that one up there. There, that looks about as clean as things can get. I like it, it's not too bad. Should go like that. So, handles accelerate, or handles adding angular impulse, torque, We'll put that in brackets because it's not torque. If you are using torque, I'm sure it's just fine. It works exactly the same way. Under acceleration and setting, B is accelerating to true/false. And then we have mouse wheel down and mouse wheel. I'm just going to leave that since that's basic. Camera, zoom in, out, comment. Be good coders even if we're not coding. Let's make sure that's all nice and neat too. So now we need to calculate our torque. So what we're going to do is we're going to create an event tick. So just right click and event tick and align it nicely with all our stuff we're making, and then hold down S and click to make a sequence and add one pin, so you have 0, 1, 2, 3 events, and connect it up, and then reroute delta seconds up and way down. And what we want to do is we want to drag in engine torque curve as a getter, so hold down control and then drag off it and type in get float value. So as you can see, you can input a time, or in our case an RPM, and it'll return a value, or in our case a Newton centimeters torque value. So we're going to use that. So all you're going to do is just plug in your RPM into InTime, and this will give us our current torque. I put current torque in curly brackets because I always do that for placeholders and blueprints, for whatever RPM, aka time. So that is going to be where we get torque. In fact, I want to make that kind of a light blue color just so that we know it's important. So the first thing we're going to do in our sequence 0 is we're going to go into a branch. So our condition is going to be an AND Boolean. And we're going to check two things. We're going to check B is accelerating, and an AND Boolean node only returns true if both of its complements are true. So both of them are true. So the second one is going to be, is RPM less than or equal to float, less than or equal to float, RPM limit. So is our RPM less than or equal to RPM limit? If it's at our RPM limit or equal to it, then we go down the false path. So we're checking both of these. So are we accelerating, and RPM does not equal RPM limit. So if true, then that means we're accelerating, and we want to set RPM to acceleration factor times delta seconds. So just float times float. So whoops, Control Z, set RPM to acceleration factor, I can't see, times time dot delta time. Yeah, let's go like that. Then we're gonna go if false. So if either we're not accelerating, actually I'm gonna put this in this branch. So if de-accelerating or at RPM limit, then we do a new go into a new branch, obviously, and what we're going to check is RPM nearly equal. So just drag off RPM and type in nearly equal float. Is it nearly equal? And B is going to be idle RPM. Now our error tolerance is going to be our acceleration factor divided by 100. So it's going to be 60. Now, I'm doing that because I run at about 60 frames per second while I'm recording, 70 whatever. So in that case, I would change this. In fact, sorry. Yeah, because I'm getting about 60 frames per second. So you basically want to your error tolerance to be about how many frames per second you're getting. And if you find that you're getting negative RPMs, then that means your error tolerance is too close and you want to make your division a little bit smaller. So basically you'd want your error tolerance to be a little bit bigger. You know, I'd maybe want to go to 100 instead of 60 or whatever. So you can always debug that by adding another sequence and then just doing a print string and then just print out RPM. And if you ever find it going into the negatives, then this is where you fix it. You fix right here. Your acceleration factor. You want your acceleration factor to be a larger, or you want, sorry, your error tolerance to be a larger number. So that's our condition. RPM is nearly equal to idle RPM within our error tolerance. So if deaccelerating or at RPM limit is false, so if we're not at idle RPM, then we set RPM. What we're doing here is we're doing the inverse of this. So basically this is aka increase RPM slowly. Well, not slowly, but increase RPM at a certain rate. And you can change that rate, by the way, with your acceleration factor. So what we're doing here is we are setting RPM lower, aka setting RPM lower at a certain rate. RPM back down. So what we're going to do is we're going to set RPM to RPM minus acceleration factor times delta seconds. And you can also just do, if you don't want to reroute, you can also just get delta seconds, get world delta seconds. It gives you the same value. In fact, I probably should have done that, but I prefer reroutes usually. So all we're doing there is we're increasing the RPM over a set period of time, and here we're decreasing it over a set period of time. So increase / decrease RPM if allowed is that whole setup there. Then our second one and our third one, very, very easy. So our second one, so the next one, is we're going to set our engine torque to whatever our current gear is times our current torque value. So all we do is we take current gear, multiply it by a float, and just get the float value, what we did up here for our get engine or get current torque for XXX RPM, aka time, and then just set engine torque to that value. So we're just multiplying whatever our torque is at our current RPM by our current gear. So again, it's still very basic. We still haven't made a transmission, but at least we have variable torque now. And then our third one is we type in, or first of all, we hold Alt and drag out current velocity. So that's our third one, or our second one. I don't know why I created that third. Oh, right, for the debug. Our current velocity, we're gonna set it. So what we're gonna do is we're gonna type in get velocity and make sure the target is actor, and that'll be in centimeters a second, but we'll do the math in our HUD. And then the target is just gonna be a reference to self. So let's see here. Let's straighten these all out. So set curve velocity to velocity vector 3 of this actor. Like so. So that is our car setup at this point. So I call this car version 2.0. So now we need to change our HUD. So after you save that, everything will work, but we're not really gonna know it. We need to update our HUD. So all I did was added one more text component. Again, make sure it's size to content. And I just put speed in kilometers an hour in curly brackets. Again, I use curly brackets for placeholders. I forgot to do that down here. Then you can go and just hit create binding, but since we're doing something very simple to these other two functions, I find it easier to just duplicate them. So what we're going to do to get current speed is we're going to do the exact same thing. We're going to get player pawn, we're going to cast to BP simple car, then we're going to drag off and get current velocity, then we're going to drag off current velocity and get vector length. So that gives us a single value in centimeters. So this gives us velocity in centimeters. And all you can type in is vector length. That gives us a float. Then we divide it by 100 to get meters. And then we divide it by 1,000 to get kilometers. And how that works is obviously there's 100 centimeters in a meter and 1,000 meters in a kilometer. Then we want to multiply a float by a float. And what we're going to multiply is, let me just clean this up a little bit. What we're going to multiply it by is 3,600. Why 3,600? That's 60 seconds in a minute times 60 minutes in an hour. And what we do to get our variable time to figure out 1 second basically, because here we have seconds, or yeah, how many minutes in an hour and how many seconds in a minute, but how do we get 1 second? Well, we get world delta seconds, so that way it's frame rate independent, so that's how long one frame takes, and then we multiply it by our frame rate. So ideally you would promote this to a variable called FPS, and you would set that every single frame to your frame rate. You'd probably need to create a C++ BP function library and expose it to blueprints. But I know I'm getting about 65, 75 frames per second, so you just need to set that to your frame rate. So yeah, again, ideally in the ideal world you want to make something better to do that calculation, and there are other ways, but that just works to get a rough guesstimate. It's not like we're needing within, you know, a half kilometer accuracy. And then we take that float and we just plug it into our text, or our format text, and we just go speed is, and in curly brackets, velocity, and then a space, and then kilometers an hour. And our toText float node, all we do is I set the maximum fractional digits to 0 usually, or 1 if you want half kilometers an hour. So I prefer setting it to 0 because I find it cleaner. So yeah, just compile that and then go back into your designer, select your text block, and just choose get current speed or whatever you called it. Compile, save, and we are ready to rock and roll. So yeah, now we have, we can still zoom in and out, we can still move the camera around, we can hit tab to switch views at any time, we can still gear up, and you'll see we have idle torque, and then we can accelerate. And one last thing, very important, I almost forgot. Create a new physical material. So right click, physics, physical material, and call it sticky tires. I'll make another one right now just to show you how to do it. And we want a friction, because before, remember, our wheels would just spin and spin and spin and spin and spin. That's because you not only have the friction of the tires that we set, but of whatever it's on. In this mesh case, it's set to nothing. So what we're going to do to fix it is we're going to override it. So set the friction to something like 10 I used, and then we want to override the combine mode. And what the combine mode is it combines the friction of your mesh, in this case our wheel, and whatever it's on. In this case it'd be this floor 2 static mesh, which has nothing. So check off override friction combine mode, and then just choose max. Now I'll choose the maximum one. So if your mesh has more friction, great in our case, because we're just testing. Otherwise we'll get 10. And then we want restitution. This time we want minimum, because we want 0. We want no bounciness as we're testing. The rest you can leave all the same. So just save that, then go to your meshes, go to your wheel, and go down to static mesh settings, simple collision, physical material, and choose sticky tires, and you're good to go. And then just hit save. And if you want more friction for debugging, you can set your testing floor, you can set its physics material too, and then you'll be sure that everything has good friction. So yeah, like I said, we have it. We'll go from this view. So yeah, we can gear up and we can go ahead and drive, and you can see our speed goes up. But you'll notice our speed doesn't go down as we turn. We don't get stuck on bumps as easy. But you will notice that if we turn at high speeds, the friction on the wheels catches. Let's see if I can get it. And we start to roll and tip. And we go on 2 wheels. And our wheels start to bug out, and then we flip over. And you ask, well, what the heck? Why is that happening? Well, you go take a car at 15 degrees steering angle or wheel angle and try driving at 25 miles an hour, and it's gonna flip over too if you don't have a modern car. And how we fix that is with a anti-roll bar, and what that does is it takes the suspension, and basically if our right wheel moves up, then we apply force down on the left wheel. So it just prevents it from rolling, basically. But that involves a suspension, which we'll have to calculate, and we'll have to change our physics assets to allow. We'll have to create the anti-roll bar. So I created a little note for ourselves here for some things that we can simulate in the future. And if you guys have any ideas for more things you'd like to see, let me know. So we need to simulate an open differential, because right now ours is a limited slip. Right now we have equal torque going to each wheel. And when we're turning, we want our wheels to be able to turn at different speed. That's another reason why we're skidding and flipping and not steering so well, because an open differential, like 99% of cars except for race cars that go in a straight line have, allows one wheel to spin faster than the other. And then on that matter, we need a final gear ratio for our differential, and then we'll need a transmission for our gear ratios. We'll need a suspension, and once we have a suspension, we're going to need anti-roll bars. And like I said, it just applies equal force down on an opposite wheel when one lifts. And then we're going to need a steering curve so that we don't just immediately go to full steering, but we can actually simulate a steering wheel with the keyboard. And in the future, maybe use RAM as plugin for joysticks, so we can use an actual steering wheel. Like a Logitech G27 or G25, G29. So yeah, anything else you guys want to simulate, let me know. So that is what I am calling the medium car. We now have an actual, you can see our torque. We have idle torque, basically that's like engine on, and it goes up as we hold down accelerate, and when we let go, it goes back down. We don't have braking yet, so that would be the next thing. In fact, because of the way I have it set up, holding down reverse actually increases the torque. It doesn't make us go forward, but it does increase the engine torque technically. But yeah, so that's it. Thanks for watching. If you learned something, please like the video, subscribe. As well, we take donations at paypal.me/BlenderTek. If you dislike this video, please tell us why. So we'll see you next time. Remember, Create your